Okay, so if you were in class today, when we had our little bit of time when technology was working, you kind of heard this. If you were not, then I wanted to go over it because I did forget to record those couple minutes. So we're talking about Platonic solids. We talked about them a little bit before. In a Platonic solid, every face is the same shape, and every face is a regular polygon. So a regular polygon means that all sides of that polygon are the same size. So like an equilateral triangle is a regular polygon because all those sides are the same. A cube, this actually should be, sorry, this should say square, not cube, is the side, right, rather than a rectangle. So if we made a shape where they were all rectangles, it's just not a Platonic solid. And in a Platonic solid, every face has to be the same shape. And the same number of faces meet at each vertex. So I have little examples of all of them, but I did not bring all of them home because some of them are a little bit big. So I have 3 of them with me. And when I link this video, I'll also link a website. I think we looked at it a little bit the other day, where they have a like animated version of each of them. So this is a tetrahedron. So tetra, just like quadra or quad, can mean 4. So this has 4 sides. So you can see a red, a yellow, a green, and then on the bottom another green. And each of these sides is an equilateral triangle. So it's made of only equilateral triangles. And all of them are, every face is the same. So it's not like a pyramid that has a square on the bottom and then triangles up the sides. Every side is the same. Then this one is called an octahedron. So octa, like octopus, means 8, right? So this, again, is made of all equilateral triangles. So we have equilateral triangles here. We have 4 that kind of come around the top if I'm holding it this way, and then 4 that are on the bottom. But you see, any vertex has 4 of these equilateral triangles coming together at that vertex. And then this one is a cube. So each face is a square. These little cutouts are just how they lock together. So each face is the same. So this is also a Platonic solid. Okay, the other 2 Platonic solids, which I will show you again in that video or in the website, are called an icosahedron and a dodecahedron, or a dodecagon, sorry. So the icosahedron is also made up of equilateral triangles, and instead of 4 coming together at each spot, there are 5. So it's as if we opened it out a little bit and had one more triangle there. There are 5 on the top, 5 on the bottom, and then a kind of a line of them around the side. So it's a little bit easier. There'll be that website, and then next class I'll try to bring it in also just to show you. And then the last one, the dodecahedron, is made up of pentagons. So a regular pentagon, which is a 5-sided shape. So looks something like this. And all of the sides are those, and we have 12 of those that come together to make this shape. So what we're going to talk about today is why is it that we only have 5 Platonic solids? And we're going to look at the numbers behind it, at the values of the angles, okay? You do not need to be able to recreate all of this on your own, but I do want you to kind of understand in general why we can't just make an infinite number of Platonic solids. So what we can think about too, and we talked about in class a little bit. So let's say I have these squares, and I put 4 squares together, okay? Well, they're coming together around this point or this vertex, but there's no empty space. So I can kind of do this, but I can't really make a shape out of that, right? I can't bend it, fold it to make a shape, because if I have these squares, we know that the corner of each square is 90 degrees. 90 times 4 is 360, and 360 degrees takes up that whole vertex, right? Around a point, it's going to be 360 degrees. So if I fill up that whole 360 degrees, I can't really turn this into a shape. Now if I take one of these squares out, so I only have 3, now I can fold it, right? I can use that extra space here to fold it down, and this is when I get the beginning of that cube. So my 90, my 90, my 90 that I had here, the 3 of them, only make 270. I have a little bit of space here that allows me to fold it. Okay, and similarly, if I look at my tetrahedron, I'm going to take this guy apart. So if I think about this being the vertex and I have these 3, they don't take up the whole vertex, so I have space to be able to fold that. Even if I put 4 of them on here, I still have space where I can fold it. That's what my octahedron looks like. And if I take one of these guys out of the octahedron for a minute, I can put 5 equilateral triangles together, still have some space. I can still fold this to make a shape. This is what my icosahedron top and bottom look like. Okay, so there's still enough play that I can do that. Now, if instead I added the 6th one in here, so I have 6 of these here, well, now I can't bend it down in a way to make a shape, right? Kind of folds up or it just makes a line, and it's because there's not any of that space, okay? We'll look in a minute that in an equilateral triangle, each angle is 60 degrees, so if I have 6 of them, 6 times 60 is 360. I've used up all that 360 degrees. All I can do is keep it flat. I have to take one of them out in order to have some play in it so that I can make another shape. Okay, and that's really the idea behind this is how many of these shapes can I make around a specific vertex before I'm out of space. And I can put 6 in here, but we can see that I couldn't even put 7, right? I can't even fit a 7th one in here, so that's definitely not going to be possible. All right, so that's what this little grid here is. So let's say we want 3 triangles, 3 equilateral triangles, to meet around a vertex. So I want these 3 here to meet around a vertex, which is what our tetrahedron looks like, right? So these are equilateral triangles. What's the sum of the interior angles of each face? So each face is an equilateral triangle. And we know that for any triangle, the sum of the interior angles is going to be, oops, not 360, sorry, is going to be 180 degrees. So for any triangle, the sum of the angles is 180. What's the measure of each interior angle? So I want to take that 180 degrees divided by 3 angles because it's a triangle. Sorry, this would. So these 3 have to add up to 180. Because it's regular, all the sides are the same. That means all the angles are the same too. So this means each angle is 60 degrees. So when I have these 3 angles, these 3 triangles coming together, there are going to be 3 triangles times 60 degrees from each triangle. This one's 60, this one's 60, this one's 60. That's going to be 180 degrees. So is this shape possible? Well, it's possible if this is less than or equal, or sorry, actually just less than 360 degrees. It gives me that little bit of play to be able to move these into a shape. And if I did this so every one of these vertices had 3 triangles coming to meet it, then this is the shape I would get. Okay, so there are 3 here, 3 here, 3 here, 3 here. So is this shape possible? Yes. And in this case, its name is a tetrahedron. So can I put 3 triangles around a vertex? Yes, because it doesn't take up all of the angles, all the angle measures, so I have some left over to be able to move it, and it's a tetrahedron. Okay, let's say we want to put 3 squares together around a vertex. So we kind of talked about this already, okay? So they're each a square. What's the sum of the interior angles of each face? Well, a square, we know, has a sum of 360 degrees. We also can remember that it's n minus 2 times 180. We had figured that out before when we drew those lines to make triangles. So if we make a triangle, 180, 180, it's going to be 360. The measure of each interior angle. So there are 4 angles. They're all the same because it's a square. So we take this 360 and we divide it by 4 angles. And each angle is going to be 90 degrees, which we already know for a square. And then when we put these together, so a 90, a 90, and a 90 is going to be 3 times 90 is going to equal 270 degrees. So is this shape possible? Yes, as long as we have less than 360 there, so then we can pull it down to make a shape. And if we do this, and we do it on all of the vertices, then what we end up with is our cube. So it is possible to have 3 squares coming together at a vertex, because 90, 90, 90 is only 270. So yes, and this is a cube. Okay, I'm going to stop this video for right now just because I want to have a couple of different segments of it so it's not quite so long for you to watch, and then I will pick it up with the next part on that page.